grand challenge in itself in AI research to try to do well on. The other type of problem are deceptive problems, where the reward function is actually lying to you. It's telling you the wrong thing to do vis-a-vis getting the globally optimal policy. So for example, in this maze here, if you start here and your reward function is distance to the goal, the reward function is telling you to go north when the actual answer is to go east. And your job is to ignore the reward function. So a classic example there is pitfall, which is a particularly challenging problem because there are very few rewards that are very far between, but there are lots of ways to get small negative rewards by hitting enemies or hitting obstacles, etc. So almost all algorithms learn to do absolutely nothing, to just stand still, because that's the way to not get all these negative rewards, which is obviously not the globally optimal strategy. So on traditional reinforcement learning algorithms get a score of 0 to about 2,500 on Montezuma's Revenge and a score of 0 or negative on Pitfall. Even planning algorithms such as Monte Carlo tree search that have access to the underlying game emulator still get a score of 0 on these games. So the typical strategy to solve these hard exploration problems is to use intrinsic motivation algorithms, which effectively reward agents for getting to new states or lowering their uncertainty. And there's been numerous attempts, including by myself, to try to use these intrinsic motivation algorithms on these games. But if you look at the performance, particularly on Montezuma's Revenge and Pitfall, you see that they help a little bit. They get scores roughly about 3,000 to 4,000 when they're done right. And recently there was 1 or 2 papers that got scores roughly about 11,000. And in one run solved level 1 of the game. So these intrinsic motivation algorithms help, but why don't they help more? Why aren't they solving the game? We hypothesize that there's one type of thing that they don't do. An intrinsic motivation algorithm in this situation might say, I'm going to take the green door and explore the entire green wing of the house, for example. But when it's done exploring that entire space, what it doesn't do is say, I should go back to that room where there were 2 doors I didn't take, because that was a promising exploration stepping stone from which I should further explore. They don't do that. So we call this problem detachment. And here's a little cartoon of how it works. Imagine that you're an agent and you start in the middle of one of these two mazes here. By chance, you may go and explore the west maze, shown here in purple, and also by chance, you may flip and start exploring the east maze, where you also find lots of intrinsic motivation. But then what happens? Afterwards, there's no intrinsic motivation over here, and you're randomly flailing around in white, not touching any green, so now you have no signal for how to further explore the problem. So we say that this algorithm has detached from this promising frontier. It's forgotten that this was an interesting space from which it could explore. So the proposal that we have is to explicitly remember promising stepping stones and where promising locations are in the space, such that we can go back to them and explore from them. And we'll show you how to do that. Another problem plaguing these intrinsic motivation algorithms is called derailment, or we call it derailment. And it's the idea shown in this example. Imagine if you had an agent that could get all the way to here, which is extremely impressive. Sorry, this is skipping ahead. Imagine if you had an agent that could get all the way to here. What most RL algorithms would do is say, oh, that was a promising new spot. I should do that again. So they'll take the policy or the agent that could get here, and they'll run it again. But they want it to do something slightly different because it fell off here. And so they'll randomly perturb the policy either with parameter space noise or action space noise. But this, if you think about it, is going to derail the agent from ever even getting back here. Most random perturbations to this policy will cause the agent to fall off the wall. And that problem gets worse the longer, more complex, and more precise the sequence of actions that's required to get to that extremely challenging place. So what you want to do is get back to this thing first, then explore from it. And that's one of the insights behind Go Explore. Now, you might counter, well, if you do that, if you get back to here first with no exploration, no stochastic perturbations, and then explore from here, you will hurt the robustness and the reliability of this policy. And I agree. However, remember, we're still exploring. We don't know if the reward is up here or over here or over here. So our philosophy is, let's first try to solve the problem, figure out exactly what it is to do. That's stage 1. Stage 2 is then to pay some extra cost to robustify only the policy that we know leads to high reward. So we're only going to pay that cost at the end once we know how to solve this problem. So Go Explore, therefore, I don't know if you saw that, but it divides this problem into 2 phases. Phase 1, first solve the problem, and phase 2, robustify. So here's how phase 1 looks. We're going to initialize the algorithm by just starting in the starting location and taking a couple random actions. And if we get to any interesting new states, which you can barely see here, we'll add them to an archive. Then we'll run the following steps on loop. We pick one of the interesting states that we visited, say this one. We will first go back to it without adding any exploration whatsoever, and then we will explore from it. And if we discover new states, we will add those to our archive, and then we'll rinse and repeat. One important caveat is that if we get back to a cell we've already visited before, but in a better way, which is like a shorter trajectory or a higher performing trajectory, we'll store that as the path that gets us to that cell. So we'll swap in the better solution. So this avoids detachment because it explicitly remembers the promising stepping stones that we visited, so we can always go back to them and explore from them. So if you contrast intrinsic motivation and go explore, I think about intrinsic motivation as like a narrow flashlight beam, that it looks in one part of the house and then moves to another part of the house and then moves to the other part of the house, always kind of moving through the house with narrow focus. Go explore, in contrast, is like turning the lights on in the living room, and then the lights on in the neighboring rooms, and then those neighboring rooms, and then the neighboring rooms of those rooms until the entire house is fully illuminated, and you expand your sphere of knowledge. So we can't run this algorithm in the original high-dimensional space because there's too many states, so we can